All right, the recording is going, so let's start off with a prayer real quick. In the name of the Father, and the Son, and the Holy Spirit, amen. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Amen. In the name of the Father, and the Son, and the Holy Spirit, amen. All right, so go ahead and have at it. So I'll give you guys 4 minutes on this one. Alright, you guys, so I'm going to go ahead and go through the answers with you now. And so after I go through the answers, then I will give you guys time to ask any questions you might have. So biles are typically derived from which class of lipids? The first question here. All right, well, bile acids, they always have this sort of structure to them. Might help you. All right, so this is the basic structure of a steroid. All right, so bile acids are all derived from cholesterols or steroids. You can say either one of them there. All right, so that is basically it for number one. So bile acids are derived from which class of lipids? I would say I'd accept cholesterol, steroids, or even if you said isoprenoids there, all those would be correct answers. All right, the second question. What is the typical charge of a bile acid physiological pH? Now, this gets into the function of bile acids. So if you remember this R group at the top here, at the very end of it has one of two things on it, right? Depending on which kind of bile acid. Either has a carboxylic acid or it has a sulfate on it. All right, it'll have one of these two groups on it. And so in either case, they're both going to be negatively charged at physiological pH. So bile acids will have a -1 charge at physiological pH. The rest of all the other R groups on this are basically neutral things like hydroxyls or methyl groups. All right, now the third question then, what is the typical role of biles in our body? All right, so there are kind of two different roles I would accept here. One of the roles is in digestion. Where our bile acids, they serve to basically help solubilize fats in our diet and make them available to enzymes like lipases or available for absorption, degradation and absorption. So bile acids help to solubilize fats in our digestive tract because they're basically soap molecules. They have a hydrophobic end and a hydrophilic end with that a -1 charge on them. The second role I would accept here is that bile acids are a way for our body to excrete cholesterol. So our liver basically takes cholesterol and metabolizes it into bile acids. So it's a way one of the ways our body has any way of removing cholesterol. So I'd accept that as well as an answer. All right, so let's go on to our second slide. Or anyone have any questions real quick? Oh, for number two, the answer is -1, Joe, because it doesn't have both of these groups. It'll have one or the other of those groups on it, not both. So it'll either have a sulfate or a carboxylic acid there. Any other questions? All right, then let's continue on to the next one. So this one, I will give you guys another 4-minute question on this one. So here we go. Alright, you guys, I'm back. So, hopefully you guys got through most of these. Alright, so, let's talk about them. So, obviously there's a bunch of questions on here about several on here about lipases. So let's start off our explanation by talking about what a lipase is. So lipases, they're a class of enzymes whose role it is to take triglycerides and cleave them. It's an oxygen there, sorry. So normally our triglycerides, if you recall, we have a glycerol backbone. Here's our glycerol backbone. And then we have 3 fatty acids that are connected to that by ester linkages. So this is a triglyceride. All right, now the role of a lipase is to cleave the fatty acids off of the triglyceride. Now, anytime we have a reaction that in biochem where we're talking about cleaving a molecule, this isn't universally true, but for the most part it's true. All right, the type of reaction that enzyme is doing is a hydrolysis reaction. All right, so you may also remember this from OChem. How do we cleave esters into alcohols and carboxylic acids? We do it by hydrolyzing them. Another way to think about this is what are the products? Well, the products of cleaving an ester are a carboxylic acid on one end and an alcohol on the other. Well, what did we just add as we broke this? We added on 2 hydrogens and an oxygen. That's water. So we're using water to break a bond. So the answer for number 1 is hydrolysis. All right, number 2, you may not have realized it at the time, but number 2 is actually about lipases as well, because it says in order for triglycerides to be absorbed by our intestinal epithelium, those are the cells that line our intestine, right, what must occur in our digestive tract? And the answer is our triglycerides must be cleaved into fatty acids and monoacylglycerols. So basically 2 of these fatty acids get cleaved off by lipases. So a lipase is in our digestive tract will basically take a triglyceride and cleave off 2 of the fatty acids and leave us with one, I'll just abbreviate here, monoacylglycerol. Now the monoacylglycerol, I'll erase some of this and just show you what that would look like. So if we cleave off 2 of these, every time we cleave one off, we get a hydroxyl group there. All right, and so this right here would be a monoacylglycerol. All right, and so that's basically now able to be absorbed into our, both the monoacylglycerol and the free fatty acids are able to be absorbed into our intestinal epithelium. So that's it for number 2. So number 2, the answer is basically it must be cleaved by a lipase. Sorry, I see some questions here. Just check. Oh, wait. Oh, never mind. No questions. That's the old question. All right, number 3. All right, how are free fatty acids transported in our bloodstream? Now, the answer for this one is this is a little bit of a tricky question, because some of you guys, I'm guessing, would have been tempted to put as a lipoprotein. And if you did put a lipoprotein, or one of the subclasses, you might have put chylomicrons or LDLs or HDLs, any of those type of things. All right, those are all wrong. All right, for this question. Those particles, all right, lipoproteins, are used to transport triacylglycerols or triglycerides, phospholipids, and cholesterol. Right. So this question is asking about free fatty acids. Now, free fatty acids are transported down to a protein called albumin in our bloodstream. right? So usually what happens is the lipoproteins, as they're going through our bloodstream, lipases release fatty acids from the triglycerides in our lipoproteins, giving us fatty acids, and those fatty acids then get bound to albumin and carried through our bloodstream. So that's it for number 3. Right. For number 4 is asking about the role of the catalytic triad in lipase. So lipase, one of the things I mentioned about it is that it functions in a manner extremely similarly to another enzyme we learned about, are serine proteases. So it's very, very similar to a serine protease. And in serine proteases, we have this thing called a catalytic triad, where we have an aspartate residue, a histidine, and then we have a serine. All right, so the role of the catalytic triad is the exact same role that it had in the serine protease. It is to make this serine into a good nucleophile. All right, so I'm going to quickly go through the mechanism here for you guys, in case you need a refresher on this. All right, at least part of the mechanism anyway. So in a lipase, if you recall, we are trying to cleave an ester bond. So this molecule down here, that's our substrate. All right, and the way these enzymes work is the serine deprotonates, or sorry, the histidine, deprotonates the serine, making it into a better nucleophile. Right? And then the serine is able to do a nucleophilic attack on its target carbonyl compound there. All right, and so what we end up with then, review, all right, we end up with an intermediate that looks like this. And then in the second step, the electrons collapse down, and we lose the alcohol group off of here. All right, so then we're left with a species that looks like this, where we have our serine covalently attached to, this is our fatty acid component here. You can tell it's the fatty acid because it still has the carbonyl on it. It's going to end up with a carboxylic acid when we cleave it. All right, and this point now, this is where a water comes in, and our histidine can deprotonate it. That makes it a better nucleophile. We can do that sort of attack there. All right, and that brings us now, go back over to this way. Just got to modify the structure slightly. All right, like this, and we can now collapse down that negative charge and cleave off our serine. So hopefully you guys see the parallels here between a serine protease and a lipase as far as how they work and how the catalytic triads are working there. So that is it for all these questions. Any questions? All right, if not, then I will continue on to the next one. So this one I will try to give you guys 5 minutes for. One thing also, I may not get through all of the questions here. We may run out of time. If we do, I will continue the recording after that, after I shut down class, and let you guys know, or post that up on YouTube so you can watch it later if you would like. All right, continue on then here. All right, you guys. So let's continue on this particular slide here. All right. So to start off with the first one here. All right, lipoproteins that are larger contain a higher percentage of the answer I was looking for is triglycerides and are less dense. All right. So the way to think about this, if you're getting a little confused or maybe just don't want to have to outright memorize everything, all right, triglycerides, their main, so they're always going to have protein, they're always going to have phospholipids, and the protein and phospholipids basically kind of make the outside type structure of the lipoprotein. All right, now the interior is going to be full of triglycerides and cholesterol. But mostly, so they all kind of contain a similar amount of cholesterol. So cholesterol is kind of similar for all of them. So that doesn't change that much. What does change, though, and go up or down, are the amount of triglycerides. All right, so basically, if they're going to be larger, right, that means they have to contain more triglycerides because that's basically going to cause them to expand in size. All right. Now, triglycerides are basically oil. So, cooking oil, stuff like that. It's basically a bunch of triglycerides. And we all know that if you mix oil and water, the oil floats because it is not very dense. So the higher the triglyceride percentage, the less dense the lipoprotein will be. All right, so hopefully that helps you out with number one if you were a little confused about it, or if you just were having problems remembering it. All right, so now moving on to our second one. All right, rank the lipoproteins in order from smallest to largest. All right, so I'm going to go ahead and provide you the answer here, and then I'll talk through how you could maybe remember this. So HDLs are our smallest, followed by LDLs, IDLs, then our VLDLs, and then our chylomicrons. All right, so this is the answer basically for number two. So smallest to largest, we'd have HDLs as the smallest and chylomicrons as the largest. Now, one of the tricky things that you will just have to memorize, right? The IDLs, they basically are always going to fall between the LDLs and the VLDLs. All right, so the intermediate density lipoproteins are actually in between very low and low. All right, I don't know why they put it there. All right, but that's where they put it. All right, so just you'll have to remember that. Now, one thing that can hopefully help you remember all this a little bit is I like to remember these actually in order of like digestion. So the chylomicrons, basically, they are involved in taking fats from our diet. So they're basically absorbing fats out of our diet, which means, if they're absorbing fats, they are going to tend to try to absorb the most energy they can. So these are going to tend to have a lot of triglycerides in them. All right, so our chylomicrons are the biggest because of what we said in the first one. They have the most triglycerides. Now, as we move to the left here, we're moving further on down in our dietary or kind of lipid transport system. And so along the way here, basically fats, triglycerides are being released to tissues, right? That's actually the role of these three here, is to release triglycerides and deliver them, and cholesterol as well, but we'll just focus on triglycerides here, deliver them to tissues in our bodies. To the point where we get to HDLs and there's basically very little triglycerides left, right? And so if you kind of remember number one and the dietary order here, that might help you with number two, possibly, I don't know. That's the way I like to think about it anyway. All right, on to number three. All right, which lipoproteins contain apolipoprotein A1? All right, so A1 is the lipoprotein that is basically targeting particles to our liver primarily. All right, and the two that are really destined for our liver are the chylomicrons and HDL at the end. So the two that are going to contain apolipoprotein A1 are going to be HDL and chylomicrons, because these are basically either taking fats from our diet and bringing them to the liver, or in the case of HDL, it's taking cholesterol from our body and bringing it to the liver. All right, number 4 then, which lipoproteins contain apolipoprotein B100? Well, that's the remaining 3 here. LDL, IDL, and VLDL all contain apolipoprotein B100. All right, this basically allows them to spend more time in the bloodstream and kind of deliver fats to other tissues in our body. All right, number 5 here. This is one that's a little bit terminology tricky. So it says describe the role of apolipoproteins. Now, apo is basically, in biochemistry, is a word that means empty. All right, so like an apoprotein would be a protein, like a normal apoprotein would be a protein that doesn't contain a cofactor or coenzyme or something like that, for instance. All right, with lipoproteins, an apolipoprotein is one that is a protein that doesn't contain the lipids. All right, so apolipoproteins do not contain cholesterol, phospholipids, or triacylglycerols. They're just the protein component of our lipoprotein. All right, so I want you, if I'm asking you to describe the structure of that, I don't want anything about the lipids, the phospholipids kind of forming a monolayer, the triglycerides being on the inside. None of that applies. All right. Now, the apolipoproteins, their structure is very alpha helical in nature. They have a lot of alpha helices, and the structure that's shown in your book, if you want to elaborate on this, I wouldn't require you guys to know this much detail, but it kind of has this sort of figure 8 type structure with these alpha helices. All right, but I would want you to know that it's mostly an alpha helical protein, and I also want you to know that in order for it to perform its function, one of its functions is to really help to make fats soluble so they can be transported. So one face of these alpha helices, kind of the outside face, is polar and charged, whereas underneath here, all right, this arrow is supposed to be under. This arrow here is supposed to be kind of on top of the helices. Underneath is very nonpolar, allowing this alpha helix to basically bind to fats, but then also on the other side to bind to water. And so like this protein here is basically wrapping itself around the nonpolar lipids. The nonpolar lipids would kind of sit on the inside here with this alpha helix wrapping around it, and the polar residues pointed outward towards the outside, helping to make this very large particle soluble. But again, the protein itself is just this sort of structure here. And just as a review, if you're a little confused about what I'm talking about with the sides of the alpha helix, so if you recall, alpha helices, the side chains stick outward from the alpha helix, kind of like a bristle brush, right? So what I'm saying here is basically one side is polar and charged, the other side is non-polar. All right, so that's it for number 5. All right, number 6, what are the roles of chylomicrons, LDL, and HDL? All right, well, chylomicrons, those are basically involved in taking fats from our diet to our liver. All right. LDLs are responsible for transporting fats and cholesterol in our bloodstream and delivering them to other tissues. HDLs, their role is to take cholesterol from other tissues and to transport it back to the liver. All right, number 7, our last one, why does LDL shrink as it travels through our blood vessels? We actually alluded to this on the previous slide, because LDLs are losing lipoproteins as they move through our bloodstream. I might have said that wrong. LDLs are losing triglycerides as they move through our bloodstream because of lipases. So lipase enzymes are delipidating LDLs as they move through our bloodstream, causing them to basically lose free fatty acids and monoacylglycerols to our bloodstream, and this then causes them to shrink in size. And that's it for number 7. Anyone have any questions before we move on? if you do have questions, you can always put them in the chat. Otherwise, here's the next series. Alright, you guys. So we're on to, oh, sorry, I accidentally advanced the slide. My bad. Alright, so let's run through these ones pretty quickly here. Alright, a single round of beta oxidation produces what? Now, the term beta oxidation, hopefully you guys know this, is on the process of fatty acid breakdown. Right? So a single round of beta oxidation is going to take our fatty acid, right, and with N carbons on it, and it's going to turn it into a fatty acid with N-2 carbons on it. So the 2 carbons are going to be lost from this, and those 2 carbons have to go somewhere. All right, they're going to go to acetyl-CoA. Right, and there are going to be other products as well along the way. We have to make an alkene, which in order to do that, we have to take an FAD. Turn it into an FADH2. Also, I should say, in order to make the CoA, acetyl-CoA, we need a CoA on here, but that's actually not part of the question. I'll just add it on here. All right, the other part is, so if you remember the scheme for beta oxidation, right? We take our fatty acid, we make turn the alkane into an alkene, then we hydrate it with water. The water's on the reactant side. Then we take that water, the alcohol that we form, and we turn it into a ketone by oxidizing it with NAD+, turning that into, on the reactant side, NADH. So a single round of beta oxidation produces all of these guys over here. Number 2, where are fatty acids broken down in a mammalian cell? Right, they're broken down in the mitochondria of the mammalian cell. Right, one thing that can help you remember that, the big product here is acetyl-CoA, which is then going to be used by the citric acid cycle. And citric acid cycle is occurring in the mitochondria. Also, the FADH2 and NADH that are being produced, they're going to be used by the electron transport chain to produce ATP. And so it just kind of makes sense for this process to be occurring in the mitochondria. All right, number 3, describe the expected symptoms for a patient with deficiency in their carnitine palmitoyl transferase 1 enzyme. All right, now carnitine, hopefully you recognize that name. All right, this is a molecule that is involved in, it basically gets attached onto our fatty acids to allow them to cross into the mitochondria. All right, and the way the carnitine gets attached onto our fatty acids is using this particular enzyme, this carnitine palmitoyl transferase enzyme. So basically, patients who have deficiencies in this enzyme are not going to be able to transport their fatty acids into their mitochondria, at least not as well as normal healthy patients. All right, so if they can't transport their fatty acids into the mitochondria, their fatty acids can't be broken down. All right, so what would the expected symptoms here be? Well, one you might expect is they would tend to have higher levels of fat in their body, right? They're going to have a hard time breaking down fats and using them for energy. You would also expect them to generally have problems with exercise and energy metabolism, right? Because if they can't break down fats, particularly under starvation conditions, because under starvation conditions, that's where we're very dependent on fat metabolism. These patients would probably really struggle to exercise under starvation conditions compared to a healthy patient. So those would be the symptoms I would say for number 3. All right, number 4, the second step in beta oxidation of saturated fatty acid produces what? All right, so let's go through. I'm just going to write the scheme here. Go from an alkane, we oxidize it to an alkene, right? Then we hydrate this to an alcohol, and then oxidize that to a ketone, and then to go back around we cleave. That's basically the scheme for beta oxidation. So the second step in beta oxidation, so this is step 1, here. Step 2 there. What does it produce? It produces an alcohol. So that is it for number 4. All right, number 5, it's asking about the mechanism of thioesterase. That's this cleavage enzyme here at the end. All right. So how does this enzyme work? All right, I'm just going to give you guys I'll go through it. All right, the mechanism of thioesterase. There's actually a cysteine that does the nucleophilic attack on which carbon. Now let's look at our structure of our fatty acid at this point. So we basically turned took our alkane, turned it into alkene, then hydrated it. All right. Then we turned that alcohol into a ketone. And that ketone is on carbon number 3 here. So the cysteine in the active site of this enzyme is going to do a nucleophilic attack on carbon. So carbon 1 is there, 2 is there, 3 is there. So carbon number 3 of the fatty acyl CoA. Right? That will push the electrons up on there. Right? In the second step, then, let me redraw this slightly. Right, in the second step, this will collapse down, basically, and what's going to be the product? We're going to cleave off this portion here. Oh, sorry, the portion on the right here. What is that? That's going to be our acetyl-CoA. As the product. All right. So at this point now, we have this structure. All right, now it says the bond to the enzyme here. This is the bond to the enzyme. It is broken in second step by nucleophilic attack by what? Well, in order to restart beta oxidation, our next round of it, we need our fatty acid attached to coenzyme A again. So the nucleophilic attack is actually going to occur by coenzyme A. And it will, in 2 steps basically. In the first step, do a nucleophilic attack, push the electrons up onto the oxygen, and for the sake of time, those will collapse down in the second step, cleaving off the enzyme cysteine here. And that is the mechanism for thioesterase. All right, you guys, I'm just going to continue on. If you have questions, put them in the chat. Yeah, we're actually not going to be able to get through all these, but we'll do this one here. And I'll actually, I'll continue on with the next ones in our next class. And yeah. Alright, you guys, so I know I'm going to be kind of short on this one because we're almost out of class time. Alright, so number one here. Alright, a single round of beta oxidation of a saturated fatty acyl-CoA can produce how much ATP using the electron transport chain? Alright, I'll also realized as I was looking at this one that I wasn't quite as specific as I should be, so I would have accepted kind of two answers for this particular one here. Alright, so a single round of beta oxidation of a saturated fat, alright, it's going to produce one NADH, one FADH2, and one acetyl-CoA. Alright, so now NADHs using the electron transport chain can give us 2.5 ATPs, and FADH2s can give us 1.5 ATPs. So a single one possible answer, if you just add these together, would be you can get 4 ATPs out of a single round of beta oxidation. Alright, now the other answer I would have accepted is some of you guys might have said, okay, the acetyl-CoA can then go on to the citric acid cycle. Alright, and in the citric acid cycle, it will give us 3 more NADHs, another FADH2, and a GTP, which is essentially the same as an ATP energetically. Alright, well, these 3 here would be 7.5 more ATPs, another FADH2, that's 1.5, and then we have our ATP equivalent over there, which is another 1. So if you include what you can get out of the citric acid cycle from the single round of beta oxidation, you basically have 10 more ATPs there for a total of 14. So I would accept either 4 or 14 given this question, the way it's worded here. On the actual exam, if I were to write this on here, I'd probably say either, the exact same question, either including the citric acid cycle or discounting the citric acid cycle. So I'll try to be more specific on that. All right, number 2 here, a single round of beta oxidation of a 2,4-dienoyl fatty acid CoA produces what products? All right, dienoyl, all right, that means it basically has 2 alkenes on it. All right, so our CoA, this is the structure we're talking about here. All right, so this is our first bond here. So we have a C8. Now, here's our second bond. So this is the 2 position. Then we'd have going down here to the 3, and then 4. All right, so this would basically be a 2,4 dienoyl CoA, fatty acyl CoA. Now you're going to have to remember this. The 3 special cases we kind of had were a 3,5 dienoyl, a 2,4 dienoyl, a 3 the fatty, or sorry, the alkene in the 3 position, or the alkene in the 2 position. Those are kind of the special cases that we can end up with when we're dealing with unsaturated fats, and you have to know how to handle each one of them. Now, the way that we handle the 2,4 is we reduce it using NADPH. So we basically are going to take the hydride here, do a nucleophilic attack, and protonate it. Sorry. And what does that give us? Sorry, I hate erasing all this stuff. All right, well, that now gives us a single double bond in the 3 position. All right, so we've already made one product here. We made an NADP+. That's one of our products. Now, once we're to here, the way we now continue is we isomerize. All right, so basically we're going to take the double bond and move it over there. So I'm just going to draw that. I'm not going to go through the mechanism right this second. All right, that doesn't really cost us anything to do an isomerization. Now at this point, right, we already have our alkene here, so we're not going to use FAD, right, because that we already have the alkene in the proper position there. Now we're ready to just do everything else. So we don't get FADH2 as a product. So no FAD is being used here. All right, instead we would hydrate this. All right, and then we would oxidize that, producing NADH. So that's another one of our products. And then we would cleave this using thioesterase. And so the products of a single round of beta oxidation of a 2,4-dienoyl-CoA would be NADP plus, NADH, and acetyl-CoA. All right, number 3. A fatty acyl-CoA has a double bond between the alpha and beta carbons. What happens next to degrade the fat? All right, so here's our fatty acid here. We'll start with this structure here. Now we also have to know kind of the names of the carbons here. So the alpha carbon is going to be the one that is right next to the carbonyl. Right, so that would be the alpha carbon. This is the beta carbon here. It says there's a double bond between those two. So we have a double bond right there. Well, that's the proper position for normal beta oxidation. So what happens next is hydration. So we hydrate carbon number 3. That's the answer for number 3 there, giving us that product. All right, number 4, odd chain fatty acids get degraded into what 2 molecules? Well, basically, odd chain fatty acids will normally get broken down in the exact same way as a even number fatty acid, producing acetyl-CoA. So we'll produce a lot of acetyl-CoA even with our odd chain fatty acids. But at the very, very end, we end up producing a slightly different species because once we have only 3 carbons left, we now have another molecule called propionyl. Sorry, there we go. CoA. All right, so our products that we would get out are acetyl-CoA and propionyl-CoA. We get both of these products out of the degradation of a odd chain fatty acid. And that is it for this one. Now, if you guys have any questions, you can leave them here. Also, I'd be interested in your comments about like if you thought this was a good format for this type of class, or if you have suggestions or anything, you can leave those in the comments here. I'm going to stay on here. If you guys want to stay on, you're more than welcome to. If you have other classes, I understand. But I'm going to continue recording for the remaining slides here. So those of you guys who can't stay or don't want to stay can always pick this up on YouTube another day. Right. Anyways, I'm going to move on here to the next one. All right. And since this is no longer class time here, I'm not going to give as much time on this, the waiting part here, but you can try it if you would like to stay. So I'll give you guys maybe a minute or 2 if you do stay. Alright, so continuing on here then. So this slide is all about ketone bodies. So the first one, how many carbons are in HMG-CoA? Right, discounting the one any there in the CoA part. Alright, so if you remember, our our ketone bodies are all synthesized. The compounds in ketone bodies are synthesized from acetyl-CoA. Basically, ketone bodies are our body's way of carrying acetyl-CoA from one tissue to another. All right, so as a result, they are going to be synthesized 2 carbons at a time. Now, basically, so your answer for this one, you know, it's going to be an even number. Basically, it's going to be 2, 4, or 6. It's not going to get any larger than 6 in ketone body synthesis. Now, HMG-CoA is basically 3 acetyl-CoAs have been put together. So the answer for number 1 is that it would have 6 carbons to it. All right, the 2 main molecules that are found in ketone bodies are going to be acetoacetate sorry, let me draw the structure here. This will help me explain just one other thing. All right, this is acetoacetate, and the other one is beta-hydroxy butyrate. Alright, now the relationship between these 2 compounds basically is they're the exact same compound except at carbon number 3 here, where beta-hydroxybutyrate basically has been reduced, acetoacetate is oxidized. The other thing you might be wondering about the beta, well, again, starting with the highest priority group, the next carbon is the alpha carbon, then the one after that would be the beta carbon, hence this is beta-hydroxy, and it's 4 carbons, so bute, and it's a acid, so it's butyrate. So that's where the name beta-hydroxybutyrate comes from there. All right, so that's it for number 2. All right, number 3, explain the purpose of ketone bodies. All right, ketone bodies are basically our body's way of transporting acetyl-CoA from one tissue to another. That's really all it is for number 3. You could also, I would also accept things like that you could say that it's our body's way of transporting energy from fats to other tissues in our body, something along those lines too. All right, number 4, why are ketone bodies elevated under starvation conditions? Well, under starvation conditions, our body basically doesn't have enough glucose for our tissues to be continually using glucose as their entire energy source. Now, this is fine for some tissues like our muscle, because our muscle tissue can burn both glucose and fats pretty easily. But some tissues like our brain, however, our brain actually only burns glucose. It doesn't really burn fat at all. So our brain has to be able to get energy from fat without actually burning fat itself. And the only way it can do this is by absorbing ketone bodies. So ketone bodies are elevated under starvation conditions to supply our tissues that can't metabolize fats with energy. All right, that's it for number 4. All right, number 5, write the net reaction for the synthesis of acetoacetate from acetyl-CoA. All right, so we're trying to make this guy here. All right, so the way that this process works, all right, is we're going to add acetyl-CoAs together 2 at a time until we basically produce our acetoacetate. So we take, to begin with, all right, we're going to take 2 acetyl-CoAs, right, and we're going to get this compound called acetoacetyl-CoA. All right, and in order to do that, well, we had 2 of these CoAs. There's only 1 CoA on this molecule here that has 4 carbons on it. So we had to lose a CoA off of that. So that's one of our products down here. Then we take another acetyl-CoA. I add it in here, and we're also going to lose a CoA, because now we're making our 6 carbon compound that I actually asked about in the first question, HMG-CoA. All right, and then the HMG-CoA gets lysed, giving us acetoacetate, our product, and another acetyl-CoA. Sorry if it's getting hard to read that there. This down at the bottom here, this says acetoacetate and acetyl-CoA. All right, so what were our, so number 5 asks you to write the net reaction for the synthesis of acetoacetate from acetyl-CoA. Well, we took here for our reactants 3 acetyl-CoAs. So I'll write a reaction up here. 3 acetyl-CoAs, 3 reactants. And we got out of this a acetoacetate, we got another acetyl-CoA, and we got 2 CoAs as products. All right, so we have this acetyl-CoA here. We saw some things are the same on the left and the right. So basically this acetyl-CoA can go away, and the 3 becomes a 2. So this then is our balanced net reaction here. 2 acetyl-CoAs become an acetoacetate plus 2 CoAs. And that's it for number 5. Number 6 here, write the net reaction for the degradation of beta-hydroxybutyrate from ketone bodies. All right, well, in order to degrade our ketone bodies, beta-hydroxybutyrate, I'm just going to abbreviate here, beta-hydroxybutyrate, gets turned into acetoacetate here so we're going from an alcohol to a ketone. So we're oxidizing, which means we're producing NADH out there. Right. And NAD has to be a reactant then. All right, now, oops. Sorry, my pen, as I'm writing, sometimes the computer thinks I'm trying to swipe slides for some reason. My touch screen. All right, now what happens to acetoacetate? All right, well, acetoacetate reacts now with a molecule of succinyl-CoA to give us succinate. The whole purpose of the succinyl-CoA coming in actually is to transfer the CoA over to acetoacetate. So the succinyl-CoA is just going to lose its CoA, becoming succinate. And the acetoacetate now is acetoacetyl-CoA. All right, now this is one of the same reactants that we had in the process of making the ketone bodies. And in the process of making them, we basically took 2 acetyl-CoAs and when we were making acetoacetyl-CoA, we lost a CoA. Well, now we're going to add in a CoA to basically take the acetoacetyl-CoA and cleave it into 2 acetyl-CoAs. All right, so our net reaction here then is we have our beta hydroxybutyrate, right? We have an NAD plus as a reactant. We had succinyl-CoA as a reactant. All right, and we have down at the very bottom here another CoA as a reactant. All right, and our products then are, we get 2 acetyl-CoAs, and 2 acetyl-CoAs, a succinate, and a NADH as products. Alright, so just to review and finish that one up, our last reaction equation basically is going to be right here. So for number 6, beta hydroxybutyrate plus NAD plus succinyl-CoA plus CoA gives us 2 acetyl-CoAs, succinate, and NADH. Alright, our last one here, I'll give you about 1 minute to work on this one, and then 1 or 2 minutes, and then I will resume with the lecture part. Alright, so our last slide here. Alright, so first one here, describe how acetyl-CoA is transported out of the mitochondria. Alright, so acetyl-CoA is not directly transported out of the mitochondria. Now, the whole rationale here basically is for fatty acid synthesis to occur. Acetyl-CoA is the building block, or the kind of the initial building block, we'll say, that has to be transported out of the mitochondria where it's being produced into the cytosol where fatty acids are actually being made. They're kind of made at basically the endoplasmic reticulum, but in the cytosol for all intents and purposes, kind of the cytoplasmic side of the ER. So how is acetyl-CoA transported out of the mitochondria? Well, it's not directly transported. Instead, it is transported as citrate. So the acetyl-CoA inside of the mitochondria gets combined with oxaloacetate to form citrate. And that's done by the enzyme citrate synthase that we know from the citric acid cycle. Now, the citrate can be transported outside of the mitochondria, where it is cleaved by the enzyme ATP citrate lyase. And ATP citrate lyase then gives us oxaloacetate and acetyl-CoA outside of the mitochondria, but it uses the energy of ATP to make that reaction irreversible. All right, so that's basically how acetyl-CoA gets out of the mitochondria. Now, your textbook has a whole large scheme basically for that entire cyclic transport system. It's called the tricarboxylate transport system. The only part I really want you to understand is how the part I just described to you here in question number 1. All right, question number 2. What's the difference between malonyl-CoA and acetyl-CoA? All right, the difference here is that malonyl-CoA has an extra carbon on it, and that extra carbon is a carboxylic acid. So I'll draw here acetyl-CoA. This is acetyl-CoA. All right, malonyl-CoA has this extra carbon on it like so. All right, so that's the difference between malonyl-CoA and acetyl-CoA. So, other ways I could phrase that question would be, how many carbons are in malonyl-CoA, discounting, the CoA part, right? What extra functional group does malonyl-CoA have that acetyl-CoA doesn't? Things like that, right? So just keep that in mind for number 2. All right, number 3. Write the net reaction that is involved in the synthesis of malonyl-CoA from acetyl-CoA and what cofactor is involved. All right. So the reaction we're doing here is acetyl-CoA going to malonyl-CoA. Well, we're getting this extra carbon here as a carboxylic acid. So this is a carboxylase reaction. This is acetyl-CoA carboxylase is the enzyme that does this, ACC. Now, acetyl-CoA carboxylase, the way it does its carboxylase reaction is the exact same way other carboxylase enzymes work that we've seen before, like pyruvate carboxylase, for instance. All right, now how did it work? It took bicarbonate and energy from ATP in order to do the carboxylase reaction. So we have to add those as reactants. The carboxylate, or the bicarbonate part, becomes the carboxylic acid, and the ATP in the products gets cleaved, giving us ADP and phosphate. So this would be the net reaction for the synthesis of malonyl-CoA from acetyl-CoA. Now, the cofactor that's involved in any of these carboxylase enzymes is the cofactor biotin. So that is the other part of number 3. All right, number 4, fatty acids are synthesized attached to what molecule? All right, well, fatty acids are degraded when they're attached to CoA. Oh, that's why I just power. So you have okay, guys, I'm sorry. Alright, you guys, so the electric company just decided they were going to come unannounced and replace our electrical meter. So I lost power, which means I lost Wi-Fi. So those of you guys hanging on, sorry, I can't do anything about that at the moment. Anyway, so I'll resume and finish up this video here. Alright, so number 4 here, fatty acids are synthesized attached to what molecule? So the answer here is going to be acyl carrier protein. All right, sorry, I'm sending a message to everyone who was still in the class. Alright, so number 5 here, list the subunits of fatty acid synthase. Alright, so the subunits of fatty acid synthase are basically all the different enzyme components that are needed in order to do our fatty acid synthesis. So, what are they? Well, first of all, one of the subunits that proteins we already talked about in number 4 has to be there. So the acyl carrier protein is one of the subunits of fatty acid synthase. All right, then we've got the malonyl-CoA transferase. This is the enzyme that basically takes acetyl-CoA and adds it onto the acyl carrier protein. All right, or the malonyl-CoA and adds it onto an acyl carrier protein, either one. All right, then we've got the enzyme that's actually going to do the condensation, or basically combine our malonyl-CoA with our acetyl-CoA. All right, and that is the ketosynthase subunit. All right, once we've made this, now we have a ketone on it, and so we now need to reduce the ketone. So we have a ketone reductase. All right, and then at this point we have a hydroxy group, and we need to dehydrate. So we have a dehydratase enzyme. All right. Once we now have our alkene, we need to reduce that. So we have an enol reductase, ER. And then at this point, we now need to deal at the very, very end. So basically this can now loop back around. So once we've reduced our alkene to the alkane, we can restart this whole process here. But once we've fully built our fatty acid on the acyl carrier protein, we also need a thioesterase to cleave it off to give us a free fatty acid. So these would be all the subunits here that comprise a fatty acid synthase. All right, the last one, what order the subunits need to function in. All right, it's basically the order shown here. So the MAT basically has to transfer it over to the ACP. All right, that's transfer the acetyl-CoA or malonyl-CoA over to the ACP, basically. So that's our first enzymatic subunit. All right, then the ketosynthase, then the ketoreductase, then the dehydratase, and the enol reductase, and then at the very, very, very end, the thioesterase. So that would be it for number 6, and that is it for this problem session. Thank you guys for your time.